Distribution is very, very common in business. Not only that, not only are many variables normally distributed, but sample statistics are normally distributed. So even if a variable isn't normally distributed, if I solve for the average of that variable and then solve for another average using another sample, and from the population take sample after sample after sample and solve for average after average after average, if I look at the distribution of those averages, they will tend to a normal distribution. Anyways, the normal distribution is a continuous probability distribution that is defined by the following probability curve. F of v is equal to 1 divided by sigma, the standard deviation, multiplied by 2 pi, all multiplied by the natural logarithmic base raised to the exponent of negative v, which is the value for any particular value, or which is the value of the variable, minus the average squared divided by 2 sigma squared. So all of this is the exponent. So e raised to the exponent of the negative of the value of a particular value of the variable minus the average, the true population average squared divided by 2 sigma squared. And this is for all values of v less than infinity but greater than negative infinity. So basically what I'm saying is for any normally distributed variable, if I know what v is, I can pick a value for that variable. I can solve for the relative probability using this function. Of course, computers solve for these things automatically, and I'll show you guys how to do that in a moment. But before we're talking about grade point averages, this would be the true population grade point average. Sigma squared and sigma, these are the true measures of spread. If I know one, I know the other. But these are the true or population measures of spread. So these things are given. If I know sigma and if I know mu, the true measure of spread and the true average, well, of course, I know E, 2.71828 or something like that, and pi 3.14. I know everything besides V. V is a particular value of the variable under analysis, the normally distributed variable. I can solve for the relative probability by using this function for all values of V from negative infinity to positive infinity. If I graph this, it will look like this. So that is the normal probability distribution. So if a population is distributed according to a normal distribution, we say that that variable is normally distributed with mean mu and standard deviation sigma. The normal probability distribution is denoted by n, mu, and sigma. And this basically means that the shape of this curve depends on two things: the mean and the standard deviation. So here are two examples of normal curves. And let's give them the same mean, but different standard deviation. So that mean might be 10. But one is much more spread out than the other. And we might have a couple of normal distributions that have different means. So that might be 10, and let's say this is 20. So different means, but about the same standard deviation. Of course, that's not drawn to scale. But the point is this. we define the curve, where the shape of the curve is defined by the mean and the standard deviation. Okay, some important properties of the normal curve. It's centered on the mean, mu. The mean corresponds to the highest point on the curve. So the highest point is the mean, and we can solve for that relative probability using our normal probability distribution, probability density function. Also, the normal curve is symmetrical around the mean. In other words, 50% of the curve is above the mean and 50% of the curve is below the mean. And then finally, the total area under the curve from negative infinity to positive infinity is 1. So the population mean centers the normal curve on the real number line, and the variance measures the spread of the normal curve. So if a variable y is normally distributed with mean mu and standard deviation sigma, then the probability that y is greater than or equal to a but less than or equal to b equals the area under the normal curve with mean mu and standard deviation sigma corresponding to that interval a to b. In other words, a might be a little bit to the left of the mean and b might be a little bit farther to the right. And I can solve for the probability that a particular value of the random variable, I might say that y is normally distributed. I might standardize y and solve for v's that map to the y's. We'll talk about that later. But basically what I'm saying is that if the variable is normally distributed, and if I know what the mean and the standard deviation, or I can solve for the area in between a and b, and that's the probability that y is greater than or equal to a but less than or equal to b. So here are 3 important areas under the normal probability distribution. So I'm going to draw a normal curve, trying to draw this to scale, but not even close. So remember, the normal distribution is centered on the mean, and there are 1, 2, 3 standard deviations to the right. There are actually more than -3 and +3 standard deviations to the right and to the left of the mean. But the probability of observing a value of the variable more than 3 standard deviations from the mean is very low. And we can learn how to solve for those here in a minute. But popular areas under the curve are 3 important areas: the area in between -1 and +1 standard deviations at 68.26%. So I solve for this area. If I know what the standard deviation is, and if I know what the average is, or if I standardize the variables, in which case the mean is 0, and if I standardize the values of the variables, if I look at the area under the curve in between -1 and +1, then I will get exactly 68.26%. Well, how about the area in between -2 and +2 standard deviations? That area is approximately 95%, 95.44%. And the vast majority of the area under the normal distribution is between -3 and +3. Standard deviations of 99.73% of the area under the curve is in between -3 and +3 standard deviations from the mean. So that is 6 standard deviations, or 6 sigmas. So if you wonder where the term 6 sigma comes from, it comes from the normal distribution. All right, so let's use the frequency option. So if you look at the syntax for this command, We type in histogram, the name of the variable. We can use an optional if qualifier, an optional in qualifier, and we've got continuous and discrete options, and then options that apply in both cases. So when you see something in brackets, these are optional components of the syntax, and then everything after the comma, which is optional, is comprised of options. And then here we've got continuous options or discrete options, and then general options. So one of the options is the frequency. So we can look at the histogram and we can see the frequencies instead of the densities. And this is what it looks like. So on the horizontal axis, we see 1, 2, 3, 4, 5, 6, 7 bins. And each bin is a range of the values of the variable mileage. And we can see the frequency. We've got 49 observations, and we can see the frequency on the vertical axis. So in the histogram, the frequency of values of a variable within an interval is measured on the vertical axis. The total number of intervals or bins is on the horizontal axis, and we can use the frequency distribution to sort of see the chances of occurrence of a particular value of a variable and how the chances change from one bin to the next. And this can be more easily accomplished by looking at the relative frequency distribution. So you can see that that is an option. That's the density when we want the density on the vertical axis. So if I want to see the density, I can see that there is about a 30% chance I'm going to get a value that is in this bin range, about the same probability in this bin range, over 50% in the top bin range. So basically what it is, it's very similar to the continuous probability distributions that we studied earlier. We can use them to make probability statements. When we were looking at the normal curve, we talked about how we could use it to make probability statements. Well, you can do the same with the frequency distributions and the relative frequency distributions, which look at densities instead of frequencies. Basically, what I can do is look at this to make probability statements. So again, the relative frequency or density for a bin is simply the number, it's simply the frequency of the occurrences of values within that interval divided by the sample size. So again, if I find that there are 14 occurrences of values within a particular interval or bin, and if I've got 100 observations, then I can say, okay, the probability that I'm going to see randomly select a value that is in the range of whatever that bin width is, I know that that probability is 14%. Also, the number of intervals or bins chosen should be the smallest. Here, actually, we'll do this in smooth draw, but the number of bins chosen should be the smallest integer k, such that 2 raised to the exponent of k is greater than n. So I'm going to say this again, and we'll just sort of scratch out the example that we're working with by hand so that we can really interpret what a frequency distribution is. But the number of intervals or bins, so the number of bins or intervals on the horizontal axis, the number of basically bars chosen should be the smallest integer k, such that 2 raised to the exponent of k is greater than, and well, here n is the total number of observations. So this is the trick. You can just set 2k equal to n, and then just round up to the nearest integer. So it's the smallest integer k such that 2k is greater than n. So you can just set 2k equal to n and then round up to get that smallest integer k such that 2k is greater than n. Hopefully that makes some sense. It sounds like an SAT problem or something like that, but it's really not that bad. All right, so in our case, what does n equal? I think we had 49 observations. So in our example, n is equal to 49. So how do we determine the number of bins? We just take the number of total observations, set that equal to 2k, and then round up. So how do I solve for k in this case? Well, you have to know properties of logarithms. Again, theta determines the number of bins automatically, and that'll usually be given. But if I take the logarithm of both sides, it's k log 2 is equal to the natural log of 49. And then I can divide both sides by the natural log of 2. And I get k is equal to log 49. K is equal to log 49 divided by log 2. Or I take the natural log of 49 and I divide that to the natural log of 2, divide that by the natural log of 2, and I get 5.61. So that is equal to 5.61, and then what do? We round up to 6. So that's the number of bins that we should use, but we don't have to use that number. We can use a little bit more or a little bit less. What about the interval width? So the next question has to do with interval widths. So again, with the frequency distribution, we're just taking a variable, mileages, and we're sorting it from smallest to largest. And then we're taking that range of values and we're creating bins. And then we look at our data and we see how many observations fall in each bin, what the frequency is. And then we can take those observations in a particular bin and divide that by the total sample size to get the density. So we can look at the frequency or the density. If you don't like density, just think of the relative frequency. So it's really simple. So let's talk about the interval width. So this is pretty straightforward. Once we solve for the number of class intervals, here we solve for 6, we can get the bin length. Basically what we do is we divide the range of the data by the number of class intervals. So we take the range, the smallest from the largest value, and divide by 6, or the number of intervals. Well, how do we find that range? Remember, I can just do sum mileage, and I can see what the range is, 29.8 to 33.3. So we take that range, 33.3 minus 29.8, supposed to be an 8, and we divide that by 6, and I get 0.58, just round up to 0.6. We're getting 0.6, that's our bin width, and we get 6 intervals. So the class width is the distance between the lower limits of consecutive classes. So now we've got the class width, and that's just the distance between the lower limits of consecutive classes. So we'll see that there are 6 classes. The distance between the lower limits is the class width. Once we have the class width, you can create the first interval by adding 0.6 to the smallest value of the variable, the smallest mileage. In this case, it is 29.8. So let's see what this looks like. So the interval would be 29.8, but less than 29.8 plus 0.6, which is 30.4. Not less than or equal to, so I denote that range of data instead of using brackets. So less than or equal to, or the base of the range to the top of the range inclusive. We're going to do the base of the range to the top of the range not inclusive, so not including 30.4. So basically what I'm saying is 29.8 but less than 30.4 is the first width. So that's that first bar. 29.8 but less than 30.4. So 30.4 is the next bottom of the class width. So 30.4 but less than, so I add 0.6 to 30.4 and I get 31. And then 31 but less than 31.6, I'm not writing it all out. And then 31.6 but less than 32.2. And 32.2 but less than 32.8. And then finally the last interval is 30, that looks like a weird 3, 32.8 but less than 33.3. So these are the bin widths, and I can see what the frequency is. So I'm going to draw the frequencies. I'll just point little arrows for these two, and then I'll draw the rest to the right. And then this is beautifully written in the notes, so hopefully you have those out in front of you. But in the first bin, we've got 3. In the second bin, we've got 9. Then we have 12, 13. We have 9 in this bin. And then in the sixth bin, we have 3. So we've got 6 bins. 1, 2, 3, 4, 5, 6. And then 1, we've got 3. And then 9. And then we've got 12. And then 13, 9 again, and 3. So hopefully this sort of looks like what we're getting in Stata. We know the intervals. So what is the probability that I get a value in between, or a value greater than 31, greater than or equal to 31, but less than 31.6? What is the probability? Well, it's 12. 12 is the frequency, but the probability is 12 divided by the total number of observations in our data. So 12 divided by the total number of observations in our data, we're working with 49 observations, and that gives us about 24.45%. So the probability that I see that I randomly select a value from my data in between 31 and 31.6 non-inclusive is about 24%-ish. I'll just put about 24%. So again, if we look at the histogram in Stata, hopefully it will look something like this. So let's do the histogram again, and there you go. And if we do the histogram frequency, we've got 7 intervals here, so it's not exactly. So we can tell Stata to do 6 intervals. We can tell Stata to do 6 bins instead of 7, and then you'll see that it looks very similar. But you get the drift. Why do we do this? So that we can make probability statements to help us understand the chances of the data that we see. So if I look at a particular variable and I look at a value for that variable, is that value rare? So if I'm looking at IQ, I know the average is 100. What if I see a value equal to 147 or something like that? Well, if the standard deviation is 15, I know that seeing a value equal to 147 is extremely rare. If I see a value equal to 60, I know that that's extremely rare. So again, we can use histograms and stem and leaf diagrams to make probability statements regarding our data. And again, this just gives us more information in addition to just the average. We're looking at measures of spread. We're following a pretty standard approach. This is usually typically one of the first things that you'll do in most statistics classes is just talk about histograms and how you can graphically display information and use that to make probability statements before moving deeper into inferential analyses where we work with probability distributions, just like we're working with histograms to make probability statements. We're going to be working with continuous probability distributions to make probability statements. Okay, moving right along, let's talk about the standard normal distribution. So for every value of the independent variable, there is a standardized value for that variable. So for every y value, there is a z value. Let's just do a quick example and then I'll follow the notes a little bit more specifically. All right, let's say that we're dealing with IQ. Sorry, when I draw on my Wacom Bamboo tablet, it's making a funny noise that doesn't sound like art. Anyways, sounds like something that rhymes with art. Anyways, so here is my normal distribution. Let's say that we're going to talk about IQ. And I know that the true average of IQ is equal to 100. I know that the average IQ is equal to 100. And I also know that the standard deviation is equal to 15. And I know that there are 3 standard deviations to the right and to the left of the normal distribution. I'm going to redraw this normal distribution so that it is just a little bit easier to use. That's just too tiny. Okay. So I know that IQ is normally distributed, and I'm just going to make this bigger. So this is the distribution of the variable IQ. And I know that the average is equal to 100. I know that the standard deviation is 15. So if I go 1 standard deviation to the right, I get 115. If I go 2 standard deviations to the right, that would be about 130, 145, and then lower and lower probabilities for values greater than 145. To the left, 100 minus 15 would be 85. 85 minus 15 would be 70. And then 70 minus 15 would be 55. And then if I go to the left of that, I get lower and lower likely values. So if I tell you what the mean is, and if I tell you what the standard deviation is for a particular variable, I can make probability statements. I know that under the curve, there is about 68% in between -1 and +1 standard deviation. It's about 68%. I know that, so I can say if I randomly select somebody from the population, there's about a 70% chance that their IQ is going to be between 85 and 115. So I can make those types of probability statements. Well, what is the probability of getting something in between 74 and 132? See, we don't know that. So what we do is for any variable, we can standardize it. You can standardize a variable by subtracting out the mean. So let's say I've got IQ for a particular individual. I can subtract out the mean of IQ, and then I can divide that by the standard deviation, the true standard deviation of IQ, and this allows me to obtain a Z value. This allows me to obtain a Z value or a standardized value. So long story short, why would we standardize a variable by subtracting out the mean and dividing by the standard deviation? It's because Z values are the same for all variables. If I say, hey, listen, I'm looking at mileages data, and let's say the average miles per gallon is 32 miles per gallon, and I'm looking at a car that gets 37 miles per gallon. What's the probability of that happening? Or what's the probability of seeing 36 to 42 miles per gallon versus 22 to 28 miles per gallon? To be able to make those probability statements, it's kind of hard. What you need is a table. So if you standardize any variable and you look at those standardized values, you can say things like, you know what, if I see this value, it's 3 standard deviations to the mean, or 3 standard deviations to the right of the mean or to the left of the mean. It's pretty rare. But that makes sense if I speak in terms of standard deviations or z-values. You can tell when you normalize a value, essentially what you're doing when you subtract out the mean and you divide by the standard deviation is you're looking at how many standard deviations a particular value of the variable is from the mean. Take that full distance and divide that by standard deviation, you get 5, and that means that that particular IQ is 5 standard deviations from the mean. So we do this for one reason. We solve for z-values so that we can easily obtain probabilities. The probabilities associated with observing a particular value of a normally distributed variable or a particular range of values of a normally distributed random variable. So let's just normalize these variables very quickly, and then we'll see how we can make those probability statements using z-tables in more detail. But again, the only reason we normalize is so that we can make probability statements, so that we can make confidence interval statements. It's just to make everything easier. So for the value of 55, let's solve for the z. Well, 55 is the IQ minus the average, which is 100, divided by 15 is equal to, well, if you do the math, it's -3. What about 115? Well, 115 minus 100 is 15, divided by 15 is 1. So that's 1, this would be 2, this would be 3, this would be -1, this would be -2, and 100 minus 100 divided by 15 is 0. So we've mapped IQs to Z's, and now that we have Z's, I can use the z-table to make probabilistic statements. The z-table is standardized, and it gives me the ability to make probability statements. Well, what is the chance of seeing an IQ in between 92 and 147 or something like that? Or the area under the curve in between these 2 points. So we'll be able to do that here in just a couple of minutes. But the reason why we standardize variables, you know, we can solve for these probability values if we don't standardize the variable. We just need a table for every variable. So IQ is measured on a different scale than miles per gallon, which is measured on a different scale than Walmart profits, which is measured on a different scale than your level of anxiety or your level of happiness or some sort of a psychological construct or psychological variable. So the fact is, we normalize values of variables so that we can use one table, the z-table, instead of a million tables for a million different variables to make probability statements. So again, for every y value, there's a z value. Thus, there's a population of z values that we can map to, or that corresponds to the population of y values. So if y is randomly selected from a normally distributed population with mean mu and standard deviation sigma, the z value corresponding to the y value can be solved for using a formula just like this. What we would do is just take the y value that we observe. It's normally distributed, it's randomly selected, so it's randomly selected from a normally distributed population. We know that the mean is mu, and we know that the standard deviation is sigma. And this just tells me the number of standard deviations. This is a distance measure, and it gives me the number of standard deviations. The number of standard deviations y is from mean mu. So the standard normal distribution, if y is normally distributed with mean mu and standard deviation sigma, so the true population mean and the true population standard deviation, if y is normally distributed with mean mu and standard deviation sigma, then z is normally distributed with mean what? With mean 0 and standard deviation 1. So when we normalize the variable, the mean is scaled to 0 and the standard deviation is scaled to 1. So the standard deviation is scaled to 1. So if we subtract mu from the inequality, just bear with me for a moment, let's say that y is less than or equal to b, but greater than or equal to a. So let's subtract mu from this inequality, and let's divide by sigma. So if we subtract mu and we divide by sigma from this inequality, we're just going to do that to all of the values in the inequality. So a minus mu divided by sigma, so we're basically just solving for z values, is less than or equal to y minus mu divided by sigma, which is less than or equal to b minus mu divided by sigma. Remember, this is just, a to b, so we're mapping these a, b values to standardized z values. So essentially what we're saying is that z would be less than or equal to the z value that corresponds to the b value, which will be greater than or equal to the z value that corresponds to the a value. Hopefully that makes sense, but basically what we're saying is that instead of looking at this interval 85 to 115, we know that 100 is greater than or we know that values in this range are greater than or equal to 85 but less than or equal to 115. Well, we can map that to -1 to +1. So essentially what we're doing is just saying what we said before, and z sub a is the z value corresponding to point A. So there's a z value that corresponds to point A, and then z sub b is just the z value that corresponds to point B. So we know that the probability of observing a y value less than or equal to b but greater than or equal to a, we know that that probability is exactly equal to the probability of observing a z value less than or equal to z sub b, which is greater than or equal to z sub a. When we start to put numbers to these inequalities and probability statements, I think it'll make a little bit more sense. But again, this is just a stats review. Essentially what I'm doing is reviewing a lot of weeks of statistics in a relatively short tutorial. So feel free to ask questions if you have them. You can send me over an email or you can call anytime. All right, moving right along. All right, so let's do an example. So the question is, and this is in the notes, if the population of all mileages is normally distributed with mean mu equal to 31.5 and standard deviation equal to 0.8, what is the probability that will observe a value less than or equal to 33.1 but greater than or equal to 29.9? So 29.9. So what is the probability that will get a value greater than or equal to 29.9 but less than or equal to 33.1? So how do you do this? You solve for the z value corresponding to 29.9, and you solve for the z value corresponding to 33.1. And with this information, you would use the z table to solve for the probability of getting a value greater than or equal to 29.9 or less than or equal to 33.3. So let's solve for the z values first, and then I'll show you guys how to do this in Stata. So we're going to solve for the z values, and then we're going to plug and chug and put them in the z table. So I'm just using a calculator. You can't see it, but well, I guess I should probably do it so that you can see it. All right, so 29.9 minus the true mean. Remember, we subtract out the mean and then divide by the standard deviation. So 29.9 minus 31.5. That gives me -1.6, and then we divide that by the standard deviation, and we get negative 2. 33.1 minus 31.5 is 1.6, and we divide that by the standard deviation, and we get 2. So we get a z-value. So now we want to know the probability that we get a z less than or equal to 2, but greater than or equal to negative 2. So let's look at the z-table, and then I'll show you guys how to do this in Stata. This is a z-table. It gives you the z-value associated with the area under the curve in between 0 and that z-value. So we know that the z-values are negative 2 and 2. Okay, here's the table. So we know that the z-values are negative 2 and 2, so I go to z equal to 2.0, and I know that in between 0 and z, a z of 2, 0.4772 is the area. Now I also know that this curve is symmetrical, so the area in between 0 and negative 2 is also 0.4772. So the total area in between negative 2 and 2 is 0.4772 times 2. So that would be 0.4772 plus 0.4772, and voila, 95.44% is the answer. So the probability that I get a value in between 29.9 and 33.1 is 95.44%. Let's do this in Stata. So before we hop into Stata, remember we saw a really fancy formula for the density function. We saw a fancy formula for the f of z-value, and we said that that gives us the probability, if this is z, that gives us the probability of the relative probability of a particular z-value. And right now we're learning how to solve for these areas in between values. So we're able to get these relative probabilities and these probabilities. Well, there are Stata functions that make this possible, that make it possible to solve for these things automatically. So I'm going to type in display normal 2, and that gives me 0.9772498. That's the area under the normal curve in between negative infinity and 2. But I want the area in between negative 2 and 2. So I want the area under the normal curve in between negative 2 and 2. So I can put display normal 2 minus normal negative 2. And I get that same answer, 0.9544. Check it out. Display normal 0. Now remember, the average, the standardized, once we normalize or standardize a variable, its average is 0. So what is the area in between negative infinity and the mean? It's 50%. So I can solve for the cumulative area in between negative infinity and some value by using the display normal command. I can solve for the relative probability by using the display normal density command. This is the trick. In Stata, you have to first standardize your variable. You have to normalize. You have to subtract out the mean and divide by the standard deviation. Now, once you do that, and you get those z-values, which correspond to the, which map to the values of the variable under analysis. So if we pick a variable, grade point averages, for every GPA, there's a z-score. So if we take a sample from a population, or if we're just looking at the population, I can get a z-score for every GPA. Once I get those z-scores, I can solve for the relative probability of a particular value. So let's say the average GPA is 2.5. We normalize it. and now that average maps to a normalized value equal to 0, what is the relative probability of getting that value? Well, it's 39.89%. What is the probability of seeing a variable that is 5 times larger than or 5 standard deviations past the mean? So display normal den 5, well, it's negative 0.00001487. So you just move that decimal 6 places over. That gives you 5 zeros before the 1. Basically 0. Display normal density. Let's say we're just going 2 standard deviations. 5%. So we can solve for the density values and the cumulative values by using the normal function, or the normal density function, and the normal function in Stata. It's that easy. All right, to perform calculations in some statistical inference procedures, we need to sometimes find the z-value such that the area to its right under the standard normal curve. So we need to find the z-value such that the area to the right of the area to its right under the standard normal curve is gamma, or z associated with that area to the right. We sometimes call this a critical z value, and we compare the critical value to calculated z values to perform hypothesis tests. So again, this is just the z value associated with some area to the right. This area might be 0.025. So what z-value corresponds to an area of 2.5% under the standard normal distribution? That's z sub gamma, or the critical z-value. We'll revisit that later, or actually let's just do a quick example. Find the critical z-value that gives us 0.025 area to the right under the standard normal distribution. So let me open up my z-table. Okay, so here's the z-table, and remember, this gives us the z-value associated with the cumulative probability in between 0 and that value. So if we want 0.025% in the tail, that gives us a cumulative probability of 0.5 minus 0.025. So I want the z-value that goes from 0 all the way up to 0.4750. In other words, what is the z for which 2.5% of the area under the standard normal distribution is to the right of that value? Well, if I look at this table, I can see that 0.5 minus 0.4750 is 2.5%, or 0.025, and that is associated with a z-value equal to 1.96. So from 0 to 1.96 is the cumulative area of 0.4750. Well, I know 0.5 is in between 0 and infinity. So 0.5 minus the area up to the z-value associated with 1.96, 0.5 minus that area, 0.4750, gives me that area left in the tail. So again, this is a symmetrical curve. I know that in between z and infinity is 0.5. Well, I know that the z-value that gives me 0.4725% in between 0 and 1.96, the z-value in between 0 and I meant to say the cumulative area under the curve in between 0 and 1.96 is 0.4725. So 0.5 minus 0.4725 gives us the, 0.4750. So 0.5 minus 0.4750 gives us the 2.5%. I'm not sure what happened there, but let me fix that. That should be 0.4750. So 0.5, which is this full area, 0.5 minus the 0.4750, which is this area, the pink area. So 0.5 minus the pink area gives us the, let's say, this area right here, that 2.5%. And again, this will make more sense when we do statistical inference later. All right, make sure to read through the notes to learn about the F distribution, the chi-squared distribution. These are other distributions. Lots of statistics follow the F distribution and the chi-squared distribution. Again, we can use these distributions to make probability statements. So if I know a particular statistic has an F distribution, then I can use that information to make probability statements. If I know a particular distribution has a t distribution, which is basically like the standard normal distribution, we'll talk more about the t distribution here in a bit, but it's basically like the standard normal distribution. And if I know a statistic follows the t distribution, I can use that information to make probability statements. And if I know a statistic follows the chi-squared distribution, I can use that information, again, to make probability statements. So review those distributions in the notes packets. I've included links. I don't have time to go through every distribution, but again, it's in the notes. You're getting a really good review now. But let's move on.